Bismillahirrahmanirrahim. In this video we will see that how we can model the mechanical system. First of all, let's look at the spring. When the force F is applied, there is the displacement X in the spring, and force and displacement are related with each other with the help of this expression, where K is called the spring constant. The second thing that is commonly used in the mechanical system is the damper. When we apply the force F, the displacement of this point is X, and force and displacement are related with the help of this expression, where X dot is the derivative of the displacement, which is equal to the velocity. So F, that is the force, can be written with the help of this expression, or it can be written in terms of velocity as shown in this equation. Now let's consider a mass which is movable by applying the force. So if we apply the force F, this whole mass will get displaced, and let's suppose that the displacement is X. So the force that is acting at that mass, that will be given by this expression, F is equal to ma, where this a is the acceleration and that is equal to the derivative of the velocity, and the velocity is the derivative of the displacement. So we can write that a is double derivative of the displacement. Okay, now let's suppose that this point is also movable, this point. When we apply the force F, there will be the displacement X at this end, but at the same time this point can move. So the net displacement in the spring will be equal to X minus Y, the displacement at this end minus the displacement at this end. If K is the spring constant, then the force will be given by this expression, that is F is equal to K X minus Y. Similarly, if we consider the case of the damper and we assume that this is not fixed, rather it is movable, right? So when we apply the force F, there is the displacement X at this end, and this end is also displaced by Y. So net displacement will be X minus Y, and the net velocity across this damper, that will be X dot minus Y dot. So if B is the damping constant, so F is given by this expression, F is equal to B into X dot minus Y dot, where X dot is the velocity at this end and Y dot is the velocity is this end. Now let's see that if we have parallel combination of the springs, how we can determine the total force. So let's suppose that we have this spring having the constant K1 and another spring having the constant K2, and both of them are connected at this point, which is movable, and this point is fixed. So when we apply the force F over here, there will be the displacement, let's suppose X. So both of these springs will apply the force, will try to resist the change in their motion by applying the force in this direction. So this force, applied force, must be equal to the forces applied by these two springs. So the force applied by the spring 1 is K1X, and the force because of spring 2 is K2 into X, right? And simplifying this equation, we can write it that F is equal to K1 plus K2 into X, where K1 plus K2 can be considered as the equivalent constant of this configuration when the two springs are connected in parallel. So when the springs are connected in parallel, the net coefficient of the spring is given by this equation. Now let's suppose that the two springs are connected in series like this. So the constant of spring for first one is K1 and for second one it is K2. So when we apply the force F, this point gets displaced by X and this point get displaced by Y. So the force on first spring will be given by this equation, that F is equal to K1 into Y, because the displacement over here will be equal to Y. And these are the two different springs. It has its own constant K2 and it will apply the force according to its construction. Okay, the force that is over here across the spring 2, that is equal to the net displacement of the spring. This point is getting displaced by X and this point is getting displaced by Y. So this force will be equal to X minus Y. And the force in each spring is same as they are in series. The applied force is acting on both of springs. Okay, now taking this equation, I can write that Y is equal to F by K1, and I can eliminate this Y using this expression. So if I put Y over here, that is equal to F by K1, so I can write down this expression, and then simplifying this one, this can be written, and we can finally write the force is equal to K2 into K1 divided by K1 plus K2 into X. So this is considered as the equivalent spring constant when the springs are in series, right? So this is the equivalent spring constant, and this is basically, we can say, the parallel combination of K1 and K2. So because if you have two resistances in parallel, R1 in parallel with R2, their net can be written as R2 into R1 divided by R1 plus R2. Similarly, you can see over here, you have the product term over here, summation over here, so I can write it like that, that K2 is in parallel with K1. So this is the equivalent spring constant when the springs are in series. Now let's look at the dampers. If the dampers are in parallel, this point is movable. It is moving by X and it is displaced by Y when the force F is applied. So the force that will be applied by damper to resist this one, that is in this direction. So this force must be equal to the sum of these two forces. So F is equal to B1 into Y dot minus X dot. This is the velocity at this end and this is the velocity, X dot is the velocity at this end. So velocity difference will be defining what will be the force that will be there across the damper B1 and B2. Okay, so we can write it like this. This is the force over the damper 1 and this is the force over the damper 2. So if we take out Y dot minus X dot as a common, so we will be left with B1 plus B2, and this is said to be the equivalent damping constant. So when the dampers are in parallel, their damping constants are simply added up. And if the dampers are in series, the force in series will be same. So the force that you are going to apply, the force that will be applied by the dampers in this direction, either by this one or this one, that will be same. So the force that will be applied by this one, that is equal to the difference of these two velocities, the velocity at this point and the velocity at this point. And the force across this damper will be the difference of velocities at these 2 points. So force is given as B2 into Y dot minus Z dot for this case, because you are applying the force over here. So Y dot minus Z dot, and this must be equal to the force between these 2 points. So that is Z dot minus X dot, right? Okay, now considering this expression b2 into y dot minus z dot. So from this expression we are going to eliminate z dot, that is the intermediate point. We are going to relate x with y. So what we can do for eliminating the z dot, we can use this expression, and from here we can find out the value of z dot and we can place it over here. And after simplification you will get this expression. So in this expression we can say that this is the equivalent damping constant, right? So this is just like the expression of two resistances connected in parallel. So when the dampers are in series, their net coefficient is given by this expression, and this is the equivalent constant of this system. Okay, now let's consider a system in which we have a mass and which is connected with a spring and a damper having the damping constant B. The constant of spring is K, the mass of this object is M, and this is the fixed point. So when we apply the force F in this direction, and let's suppose that this mass will be displaced and the displacement is this x of t. So sum of all the forces acting over a body should be 0 or should be equal to applied force. So you are applying this one, so all other forces must be equal to this applied force. So we can write down the differential equation for this one. So first of all, let's look at the force. One force will be because of the mass, and that is equal to ma. So what is a? That is the double derivative of the displacement, so that will be equal to mx double dot. So that you can see over here, that is because of the mass. That will be in the opposite direction, because when you are going to apply the force, this is going to resist that change. This force must be equal to the sum of all the forces acting over this body. So one force will be applied by this spring, one force will be applied by this damper, and one force because of the mass, right? So the force because of the mass is this one, force because of the damper is this one, because that is proportional to the velocity. So b into x dot, the velocity will be determined by this one, x dot, and the spring force, that will be equal to k into x. So this force, spring force plus damping force plus the force because of the mass must be equal to the applied force. So we have this equation. Now if we take the Laplace transformation of this one and assume that there are the zero initial conditions, so we can represent this double derivative with s square, this one with s, and this one as x of s, and taking the Laplace transformation of the input, that is f of s. So I can write down this expression in the frequency domain, and if I take x as common, so I can write the expression like this. Now what is the transfer function? Transfer function is the ratio of the Laplace transform of the output with the Laplace transform of the input. So x of s is the output over here and the input is this force. So x of s over f of s is the transfer function g of s, and that is obtained by rearranging this equation, and that is equal to 1 by ms square plus bs plus k. So this is the transfer function for this system. Now you can understand this system easily if you develop the free body diagram. What is the free body diagram? It shows all the forces acting on a body of mass m. So if I represent this one with this block having the mass m, the input force is f of t that you are going to apply over this mass. There will be an opposite force that will be applied by the spring, that is kxt. Another force that will be applied by the damper, that is bx dot t or b into v, and the third force that will be applied because of the mass, that is mx double dot. So a free body diagram indicates all the forces acting over a body. So this is in time domain, and the free body diagram in the frequency domain will be represented like this. That is the Laplace transformation of this f of t, that is f of s, Laplace transformation of this one, Laplace transformation of this one, and b into x dot will be equal to bs into x of s, and mx double dot will be equal to ms square x of s, right? So this is the free body diagram which indicates all the forces which are acting over a body. So whenever you apply this force, there will be the resistive force, resistance because of this mass, resistance because of this damper, and spring, and this is the damper. You can write down the state space equation for this system by the help of the differential equation that you have considered over here. This is the differential equation defining the system. So we have already discussed it in the previous video. You can refer to that video to understand that how we can write down the state space equation for this system. So the state space representation of this system is given by this set of equation, right? So if I quickly take this equation, I can write it like that m, rather I should write it like that x double dot t is equal to minus k by m into x of t minus b by m into x dot t plus f of t, right? So now if I select the state variable, that let's suppose that y is equal to x1, and let's suppose x is equal to x1. So x dot will be equal to x1 dot, let's suppose that is equal to x2, right? And x2 double dot will be equal to x1 double dot, that will be equal to x2 dot. So I can write this x double dot like x2 dot, and that will be equal to minus k by m, x of t is equal to x1, so x1 minus b by capital M x dot t. So x dot t, from here you can write it x2. So into x2 plus u. So you have this first order differential equation that will be used to write down the state space equation. So that you can see over here, x2. This is minus k by m into x1 minus b by m into x2. This one, the constant of x2, the constant of the x2 or coefficient of x2 and the coefficient of x1, right? So you have written this equation from here, and with the input and there will be division of m as well over here. So you can see 1 by m over here, and the second equation will be written from this definition, x1 dot is equal to x2. So x1 dot is equal to x2, so that you can see over here that x1 dot, with the x1 it is 0 and with the x2 it is 1. And if we want to observe x1 at the output, so our matrix C in the state space will be 1 0. So 1 multiplied with x1, you will get the x1 at the output, right? So our output equation is y is equal to x1, and the D matrix over here is 0 because the input is not directly linked with the output. Okay, now let's look at the system, spring mass dashboard system with massless cart. So in this cart is moving and has the 0 mass. Rest of the system is exactly same that we discussed earlier. So if you push this cart and if it is displaced by applying the force U, so this will also move. So let's suppose the movement over here is y, the displacement is x. So it's a translational system, And according to Newton's law of motion, that sum of all the forces must be equal to ma, right? So what is the summation of force? Sum of forces in the direction of acceleration acting on mass m. Those forces are summed together and their sum must be equal to the force applied because of the mass itself. So we can write down the differential equation for this system, that this ma is mx y double dot, because the displacement over here is y. So m y double dot, that is the double derivative, that is equal to, that must be equal to the sum of the forces applied in the opposite direction, right? So this is the force, that is minus ky, right? But we will have to consider the net displacement. If this point is moving by y and this point is moving by u, so what is the net displacement? That is y minus u. So net displacement of the spring will be y minus u. So spring constant is k. So net force because of the spring is given by this expression, k y minus u. This is because of the spring. And now let's look at the net force because of this damper. So what that will be, this damping constant is b, and as we have considered this direction of the movement, so y dot minus u dot will be the net velocity over here. So that you can see over here, into b will be the force because of this damper, right? So sum of all the forces must be equal to 0, or sum of the forces in the direction of A acting on a mass m must be equal to ma, right? So we can write down the force equation, force balance equation for this mass. So that is equal to that ma, that is y double dot plus b into y dot minus u dot plus k y minus u, that must be equal to 0. Sum of all the forces acting on this mass should be 0, must be balanced. You can write this equation or you can write it like this, right? So rearranging this equation, I can write it like that: my double dot is equal to minus b y dot minus x dot minus k y minus u, and then collecting the y terms on one side and the u terms on the other side. So now taking the Laplace transformation of this one, ms square ys plus bs y of s plus k y of s, that must be equal to bs u of s plus k into us. For first derivative you will have s, and for double derivative you will have s square. So now if I take y of s common out from this term, I can write it like this, and if I take u of s common out, I can write it like that. So now what is the transfer function? Transfer function is the ratio of the Laplace transformation of the output with the Laplace transformation of the input. So y of s is our output, input is g of s, that is the force applied over this one, or this is displaced, basically the displacement over here, u. So y of s over u of s, that will be equal to bs plus k divided by ms square plus bs plus k. So this is the transfer function defining this mechanical system. Now let's see that how we can develop the state space representation for this system. So this is the differential equation that we have defined above. I can write this differential equation like this by dividing whole of this equation by m, that you can see over here. Now we have this differential equation b. In the previous videos we have also discussed the standard differential equation, the derivatives of the forcing function, that is given like this. This is the standard differential equation with the derivatives of the forcing function. And for this differential equation, we have seen that how we can write down the state space equations. So I am going to compare this equation with the standard equation. So if I compare, here you can see this A naught will be equal to 1 and this A1 will be equal to B by M. A2 will be equal to K by M. B naught will be equal to 0 because double derivative term is missing over here, and the B1 will be equal to B by M and B2 will be equal to K by M. So for this standard differential equation, the state space is given like that state variables x1 dot x2 dot 0 1 minus a2 minus a1 state variables plus beta 1 beta 2 into forcing function, and the output is 1 0, and here is the direct transmission matrix that is equal to beta naught. So what we need to do, we need to calculate beta 1 beta 2 and beta naught, and the definition of the beta naught from our previous video, we can write it like that beta naught is equal to B naught, B1 is equal to B1 minus A1 into beta naught, and beta 2 is equal to this expression. So what we are supposed to do, just we are going to take the values from here B1, B2, B1, B naught, A2, A1 and A naught, and we are going to place these values in this expression, and we are going to calculate B naught, beta naught, beta 1 and beta 2. So let's calculate beta naught, B1 and B2. So B naught is 0. So beta naught will be 0. Then calculating beta 1 is equal to B1 minus A1 into beta naught. So taking the values from here and plugging it over here, we will get beta 1 equal to B by M. Then calculating beta 2 will be equal to B2 minus alpha 1 beta 1 minus A2 into beta naught. So plugging in the values, you are going to get this value as the beta 2. So now we can write down the state space equation just by replacing these values. So A2 is equal to minus K by M, and in the state space form, what we have, minus of A2. So minus K by M, then minus A1, that is minus B by M, then taking the value of beta 1, so beta 1 is B by M from here, then taking the value of beta 2, and beta 2 is equal to this one from this expression. So we can write down the state space form, state space equation for this mechanical system. So we have discussed the transfer function for this mechanical system, and that was derived by writing the differential equation defining the system, and then we have seen that how we can develop the state space representation for this mechanical system. So we have seen all the three forms which we have discussed in the previous videos: state space representation, transfer function representation, and the differential equation representation.